anything that's a frequency anomaly in your laser, in the beam amplitude, will show up in the FFT. On the probe data page is the information that came out of the sensor itself. This is the chart of the wavelength corrections that are used if you turn on wavelength correction. This is a correction factor for the wavelength that you're currently using. This probe is calibrated at 1047. Now you notice it says our user wavelength down here is 0. That's because this is the first time this software has been loaded on this machine. I can change that to 1047. And our correction factor immediately jumped to unity. Now the software will remember all of these controls and settings when you exit. The first time you power the software up on a new machine, that configuration file isn't present, so it defaults. Another way to store the information is you can go to this front page and you can save and recall instrument setups. This is really useful if you have a complicated setup and you don't want to have to write a long document explaining to the technician what to do. You can simply put the software in the state you want, call that setup for test 53, and then tell the technician in the work instructions, just load setup for test 53, and the software will be in that state. Another useful thing is what we have is called the life test. What this does is it calls a VI that you can program and set up. You can tell it when you want it to start, when you want it to stop, how many pulses you want it to take in the batch, what you want the test interval to be, from seconds to hours to days, and then you can tell it to start the test. And what the software will do is it will activate itself and establish communications with the box, and it will wait until the first test is to be run. It will take tests at those intervals and store them in a file that you name. Any information that you want to put in that file on top of the information the box is storing, which is all of your pulse data as well as the setup and the state of the box when the data was taken, will be appended to it if anything you can type into this window, just so something maybe to jog your memory as to what the test was for. The other way you can run this test, and I'll demonstrate that, let's see here. I'm going to set a test interval of about 6 seconds. I'm going to tell it to get 1,000 pulses in the batch, and I'm going to tell it to start right now because I want to do something right now. I'm going to go to lunch. I'm going to tell it to go out and get 5 tests. Now it'll come back and we'll say, where do you want to put those? I'm going to call it data test 1. Maybe not. Just test 1. The reason I'm calling it test 1 is it's going to rename these files incrementally as it gets them, and I don't want it asking me each time if that's okay. I think I'm going to need a test 1 if I can see this laptop. There we go. Okay. Yes, we'll replace it. The box immediately starts taking data, tells you what it's doing with the data, tells you when the data was taken, and it's going to run 5 tests. Now if I were to abort this test, it would tell me that I had aborted the test sequence, but all the data that had been currently written up until that point will still be saved in the test file. Oh, wrong one. You can edit all this stuff out. Live test. Okay. Now in the test I told the box to store raw data. I'm going to tell it now that I want to store statistical data. And what will happen is it will ask me just what I want to store. So I'm going to store the min, the mean, the max, and the standard deviation. Now every file that it opens for each particular test will be a unique file with a numeric indicator as to which order it was opened. It doesn't make a lot of sense to do that with a statistical test because not much data is being stored, whereas in the raw test, 1,000 points were being stored. So I will tell it to put that into a single data file. We'll go back to our 1,000 tests, 1,000 pulses rather, every 6 seconds, and we'll start using the current time. We'll get 3 tests, and we'll call it stats. I'm going to run the 3 tests. And it's finished. And I can exit this right now, and I can go and find that file and look at it. Okay, cut. This is the data file that was written by that particular application. We told it to store the min, max, and the standard deviation. And there those values are, min, max, standard deviation. There's a value on the end called flags. It's this little 0 out here. If 0 is present, there were no errors. If 1 is present, you had an out of range error. If 2 is present, you had an overtemp error. If 3 is present, you had both errors. Tells you at the bottom the type of instrument you were using and the setup of the instrument and how many batches you were using in the pulse. And this again is all 3 data sets were written to the same file. I'll show you an interesting thing now with the script chart. I'm going to set the batch size back to about 100,000. And I'm going to put the laser in standby, and I'm going to arm the box. Now you notice the arm light is on, we're sitting here and nothing is happening. The box will sit here in this state until I abort it or power off the box. It's waiting for the triggers and it's waiting to get 100,000 of them. I'm going to bring the laser out of standby. And the laser came out of standby, and here the data is coming down. A little faster now because we just got 100,000 pulses. This is the startup transient of the laser, and you'll notice there's something going on right there in the very front edge. We'll zoom in on that. So the laser started, it had a few hiccups, it stopped, and then it started up again on what looks like an exponential curve. You can go to the FFT page, and sure enough, there's an exponential fall, which is the Fourier transform of an exponential rise. I want to emphasize again, any joule meter you go out on the market to purchase right now, and you want to catch every single pulse, you're talking about thousands of pulses per second, not hundreds of thousands of pulses per second. If you look at the time scale down here, this is a millisecond. All of this information is captured in less than the first 100 milliseconds. If you're using a power meter, you're never going to see this. If you're using the second fastest joule meter on the market, you might see a little bit of that. You'll never see this. This is the only instrument capable of showing you this type of information on your laser. One last feature I'm going to show you is very nice for people out in the field. I'm going to turn on wavelength compensation, and you'll see the indicator come on at the top of the screen. Go to the probe data and call this function called user probe cal. And then I'm going to ask Mach 5 to read the average power. Now the batch size and the wavelength for this function are passed in from the calling VI. So we have roughly 10 milliwatts of power. Now suppose I took my trusted power meter that I believed very strongly, and it said that I had 9 milliwatts of average power. I would type that number into the window, and I would tell Mach 5 to calculate a new response for the probe. What it's going to do is it's going to find that 532 nanometer wavelength in the response, and it's going to correct it for what I told it was there. And you notice the bump jumped up in the response. Mach 5 will then reset itself to force a reread of the probe, and now what we can do is we can read the average power. And you can see we're now reading our 9 milliwatts that we wanted. Now if you get in here and you're worried about the result, or you may have done something incorrect, you can always call this button and load a typical response back into the probe. There are a number of them in here. This is our silicon diode with no window, so I'll tell it to reload that response. All we've done is we've taken the bump back out of the curve that we put back in there and put the standard default response curves from the manufacturer back into this probe. It's going to write 40, and when it's done it's going to again reset itself to force a reread of the probe response out of the probe. And now if we redo the average power, you'll see we'll come back to our 10 milliwatts. That's very useful out in the field if you have a power meter that you trust. With fiber lasers, you would want to take some care to make sure